Hello everyone, this is Surajit and welcome to our channel. In last lecture, we have learned how to calculate electric field for any kind of arbitrary continuous charge distribution. So now we'll move forward and we'll learn how to calculate electric field for symmetric charge distribution using Gauss law. But before diving into the Gauss law, I always believe that understanding the concept of electric field lines and electric flux will always help us to grasp the idea of Gauss law much better way. So keep that in mind. In this video, we'll talk about electric field lines, their mathematical representation, their properties, as well as we'll also introduce the concept of electric flux. So let's start. So right here, electric field lines. Electric field lines. So first we'll write the definitions of electric field lines. So what is the definition? Uh, these are some imaginary line. These are some imaginary line or we can say these are some these are some imaginary curve. These are some imaginary curves which drawn in such a way so that the tangent to this curve at any point at any point gives the directions of electric field at that point. Okay, so these are some imaginary line which drawn in such a way uh, so that the tangent to this curve at any point gives the directions of electric field at that point, means where we are the point where we draw the tangent, at that point the directions of electric field will be parallel to the tangent. Okay, now based on this definition, we can represent the differential equations of this electric field lines. So then next right here, differential equations of electric field lines. Differential equation of electric field lines. Okay, so to write the differential equations of electric field lines, let me draw a simple figure here. Let's say this is our rectangular coordinate system, x, y, z. and then consider a pace curve, any arbitrary pace curve. This can be represented as r is equals to r function of s, where h is the parameter. That means it's a parametric equation of the pace curve, where actually r is function of xyz and xyz itself, xyz all are function of s, so we can write r is function of s, function of s. So let me just write this assumption here. So let's assume, let us assume r, which is function of s, represent a pace curve space curve. Now what we are arguing, that if this r is equals to rs, if this r is equals to rs, represent an electric field line lines, then according to the definition of electric field lines, we can write dr by ds, so that will give you the tangent of this curve at any point. So this tangent vector must be parallel to the electric field, because tangent component, according to definition, the tangent will give the directions of electric field. So other way we can say this tangent vector will be parallel to the electric field. And when two vectors are parallel, we can simply write, say, a vector and b vector. If they are parallel vectors, then we can write a vector is equals to some constant into b vector. The same way, if this tangent vector is parallel to the electric field at any point, then this tangent vector must be equals to some constant into electric field at that point. Now this r vector can be written as xi cap, which is function of s, y also function of s into j cap, and z as a function of s k cap. So therefore this del r by del s can be written as dx divided by ds I cap, dy divided by dz ds j cap, plus dz divided by ds k cap, ds k cap. So this is the tangent to this curve at any point. Now from this equation, dr by the tangent vector is parallel to the electric field. And also just let me write here, in general electric field can also be represented like E vector is equals to, in terms of x component, y component, z component. Let's say x component of electric field is Ex, y component of electric field is Y, and z component of electric field is Ez. So we can write E vector is equals to x component of electric field plus into I cap, then y component of electric field into j cap, plus z component of electric field into k cap. So now if we put the value of this tangent vector and the value of this electric field in the above equation, means in this equation, then what we'll get, so dr divided by ds equals to alpha into e vector. So now if we put the value of dr, this tangent vector here, what we'll get, dx divided by ds into I cap, dy divided by ds into j cap, plus dz divided by ds into k cap is equals to alpha into ex I cap plus ey j cap plus ez k cap. So now if we compare the coefficient of I cap, j cap, k cap from both sides, then we can write a three differential equation. We will get three differential equation. So right here, comparing the coefficient of I cap, j cap and k cap from both sides of the above equation. We can write what we can write simply, if we compare the coefficient of I cap, j cap, k cap from both sides, we can write dx divided by ds is equals to alpha into ex. Also we can write dy divided by ds equals to alpha into ey, and also we can write dz divided by ds is equals to alpha into ez, alpha into ez. And then if we simplify this term, or if we just simply first in the first equation, if we divided both sides by x component of electric field, and then if we multiply this ds on the right side, then what we'll get, dx divided by ex is equals to alpha into ds. Same way, from second equations we can write dy divided by ey is equals to alpha into ds. And from third equations we can write dz divided by ez is equals to alpha into ds, alpha into ds. Now take a look on the right side of these three equations. You will see all these three equations right side are equals, alpha ds, alpha ds, alpha ds. So if their right side are equal, then left side must be also equal. So from above three equation, we can write from above three equations we can write what we can write. We can write simply dx divided by ex is equals to dy divided by ey equals to dz divided by ez, dz divided by ez. So this is a first order differential equation. So this differential equations is called the differential equations of electric field. So this is the differential equations of electric field. sorry, electric field lines in rectangular coordinate system. Okay, so this is the differential equation of electric field lines in rectangular coordinate system. Okay, rectangular coordinate system. So sometimes examiner give us electric field in terms of spherical polar coordinate, and then they ask me what is the differential equations of electric field lines in spherical polar coordinate system or cylindrical coordinate system, or they can also ask what will be the electric field line equation. So if we solve this differential equation, we'll get a relations between x, y, z, and that will give us the equations of electric field line in rectangular coordinate system. So similarly in spherical polar coordinate system, if we can write these equations in terms of spherical polar coordinate system, and then if we take the integration from there, we also get some relations between r theta phi, and that will be the equations of electric field lines in spherical polar coordinate as well. And if we want to write in cylindrical coordinate, and we have to write in terms of rho phi z. So if we want to write this differential equations in other coordinate system, we can easily write that. Just for that, what we have to recall that the elementary length associated with each variables in rectangular coordinate system. So that so dx is the elementary length along associated with x, dy is the elementary length associated with y, and dz is the elementary length associated with the third variable z. Now in spherical polar coordinate system, so in spherical polar coordinate system, spherical polar coordinate system, what are the three variables? R, theta, phi. R, theta, phi. We use three variables in spherical polar coordinate system, and these are r, theta, phi. So the elementary length associated with r is dr. So dr, then this differential equations of electric field lines in spherical polar coordinate system, we can write like this way. The elementary length associated with r is dr. So dr divided by r component of electric field is equals to elemental length associated with theta, that is r d theta, divided by theta component of electric field is equals to r sine theta d phi, that is the elemental length associated with phi divided by e phi, divided by e phi. So this is the differential equations of electric field lines in spherical polar coordinate system, in spherical polar coordinate system. And if we want to write this electric field lines in cylindrical coordinate system, so in cylindrical coordinate system, so what are the three variables in cylindrical coordinate system? Rho, phi, z. So the elemental length associated with rho, that is d rho divided by e rho, and then elemental length associated with phi, that is rho d phi divided by E phi, and then associated element and Z is dz divided by Ez, divided by Ez. So these are the three this is the differential equations of electric field lines in cylindrical coordinate system. So now if we want to calculate the equations of electric field lines, then which equations we should use, that will be depends on questions. So to calculate the differential equations of electric field lines, what we have to do, we have to integrate these equations. So for that we should have the electric field. We should know the electric field. Now if in the questions if electric field is given in rectangular coordinate system, then we will use this definition of electric field lines. We'll use this differential equation and then we'll integrate, and from there we'll get the relations between x, y, z, and that will be the electric field line equation. And if the electric field is given in r theta phi, that is in spherical polar coordinate system, then we'll use this differential equation, and then when we integrate these differential equations, we'll get relations between r theta phi, and that will be the field line equations in spherical polar coordinate system. And same way, if electric field is given in cylindrical coordinate system, then we'll use this differential equation, and if we integrate, and then we'll get a relations between rho phi z, and that will be the electric field line equations of electric field line in cylindrical coordinate system. Okay, now let me some example, how we can use this differential equations, or using this differential equations, how we can calculate the electric field lines, electric field lines for different charge distribution. So let me just give some examples so that you can get this idea how we can calculate the equations of electric field line using this differential equation. So write here example 1. Example 1. Example 1. So in example 1, what we want to do, let's say we have this is our xy plane. This is, let's say, x-axis, this is y-axis, and then at the center of this xy plane, that is at the origin, we have placed a point charge q. So now this point charge q will create an electric field. So we want to write the equation of this electric field lines. So equations of this electric field lines associated with the electric field that will be generated because of this point charge. And which plane? In this case, we want to simply write it in the xy plane. XY plane. So right here, electric field equations of electric field lines for a point charge. Equation of electric field lines due to a point charge. Due to a point charge. Okay, so we have a point charge, and for that we want to write what will be the differential, or what will be the equations of this electric field line in xy plane. So for that we know the differential equations of electric field lines. We know the differential equations of electric field lines, and what is the differential equation? Is dx divided by ex is equals to dy divided by ey is equals to dz divided by ez. Dz divided by ez. So in this case we want to write the electric field equations of electric field line in the xy plane. So we can simply just write dx divided by ex is equals to dy divided by ey, because dz in this case will be 0. The xy plane dz will be 0. And so if we want to calculate this electric field line equation, if we want to write the electric field line equation, then we have to integrate this equation. But before integration, we have to put the value of x component and value of y component of electric field. So for that, let me consider some arbitrary point. Let me consider a arbitrary point, let's say P, and it has a coordinate, let's say x and y. X and y. So then what we have to do, first we have to write the electric field at this point because of this point charge. So right here the electric field at the point P due to a point charge. Due to a point charge Q is E vector is equals to, so how we can write this electric field? 1 by 4 pi epsilon naught Q divided by R cube into R vector, where this R vector is the position vector of this P with respect to origin. So in this case we can write Q divided by 4 pi epsilon naught, and then R vector, in this case it will be xi cap plus yj cap divided by modulus of R cube. So in this case it will be x square plus y square all to the power 3 by 2. All to the power 3 by 2. So if this is the electric field, then we can write x component. Therefore the x component of electric field Ex is equals to Q divided by 4 pi epsilon naught x divided by x square plus y square all to the power 3 by 2. And same way y component of electric field, and y component of electric field Ey is equals to Q divided by 4 pi epsilon naught y divided by x square plus y square all to the power 3 by 2. So now we know the x component of electric field and y component of electric field. So if we put the value of this x component of electric field and y component of electric field in the above equation, and if we take dz equals to 0, then what we'll get? So now we have this equation. So if we put this equation, put the value of dx ex y in this above equation, and if we take the dz equals to 0, so what we'll get? We'll get dx divided by Q divided by 4 pi epsilon naught into x divided by x square plus y square all to the power 3 by 2 is equals to dy divided by Q divided by 4 pi epsilon naught into y divided by x square plus y square whole to the power 3 by 2. Whole to the power 3 by 2. So now if we simplify this, then what we'll get? We'll get simply dx divided by ex is equals to dy divided by y. Dx divided by x is equals to dy divided by y. So now we have to integrate this equation. So if we integrate, then what we'll get? We'll get a ln x is equals to ln y plus some integration constant. In this case, we can write ln c, where c is some integration constant. So from here, what we'll get y is equals to some constant c prime into x, where c prime is the 1 by x, 1 by c. So this is the equations of electric field lines due to a point charge which is placed at the origin, whose the place is the origin. So this is the equations of electric field lines in the xy plane for a point charge which is placed at the origin. Placed at the origin. So now if we draw this line, so this is not a single equation. Actually, it's a set of a large number of equation. So it's a set of large number of equation, because if we take a different value of c prime, we'll get a different straight line, but every time this straight line will pass through the origin. So this represents a set of straight line which passes through the origin. So first case, if we take x equals to 0, sorry, c prime is equals to 0, this constant, if we put 0, then y will get y is equals to 0. So in this case, we'll get a, so this is the equation of x-axis, y is equals to 0. So electric field line will be like this. And same way, if we put x is equals to c prime is equals to infinite, in that case x will be 0, so it will be parallel to the y-axis. Parallel to the y-axis. And then if we put, say, c prime is equals to 1, then what we'll get y is equals to x. So it will be like this. And in opposite directions, it will be like this. And then if we say put c is equals to some, let's say, -1, then we'll get value like this. And in opposite direction also will be like this. Okay. So if we place a point charge here, because of this point charge, there will be electric field. So if we want to draw this electric field line associated with this point charge in the xy plane, so it will look like this. It will be a set of parallel lines which will passes through the origin. So practically, if we want to draw this electric field lines, so in definitions we written that is a imaginary line. So why it is imaginary? Because if we place a point charge on any plane, we'll not see any kind of like this type of line. We just to represent this electric field line, we are assuming, so these are some imaginary line, in the sense if we place this point charge in the plane, we'll not see this kind of lines. This is just an imaginary concept. Just like if we want to represent a time on our Earth surface, then also we just define the value of theta and phi, equilateral lines, and these true lines, polar lines and equilateral lines. So same way, these are also imaginary lines. On the Earth surface, we will not get that any kind of surface, any kind of line like this. So same way, when you place a point charge, you will not get a line like this. That's why I call it, these are imaginary lines. And how we can practically draw this line? For that, what we have to do, if we place a point charge, let's say plus q charge here, and then if we place a unit positive charge which is movable, then if we release this point charge at this point here, so this charge will moving along this direction. Now if we connect the path, that will give you actually this imaginary line. This imaginary line. Now if we this point charge place here, then this will move along this direction. So at this, along this direction, the electric field lines will be like this. Okay, so mathematically we got the we know how to write these differential equations. Experimentally, if we want to draw any field lines associated with any charge distribution, what we have to do, we have to place this charge here. Whatever charge distribution will be given, we have to place this charge in the space, or if it is on the plane, then we have to place the plane. and then we have to place another point charge in this electric field, in this electric field. And then since this point charge, test charge will be in this case movable, so now if we release this charge in this region, so then this charge, this positive unit charge will move along different paths. So if we connect this path, we'll get the lines. We'll get these lines, and so this way we can draw practically electric field lines. And if we want to write the mathematical equation of this electric field lines, so we can use this differential equation, and from there we can calculate what will be the electric field line equations of electric field lines. Okay, so this is one example how we can use these differential equations to calculate the electric field lines in a rectangular coordinate system. Also, let me give you another example. So using these differential equations, how we can calculate electric field lines in other coordinate system. So for that, let's assume right here example 2. Example 2. So in this case, instead of electric point charge, what we are in second example, what we want to do, we want to write the equations of electric field line due to a dipole in spherical polar coordinate system. In spherical polar coordinate system. So for that, again, let me just draw a coordinate system first. Let's say this is x-axis, this is y-axis, and this is z-axis, and we have a dipole, point dipole at the origin. The center is at the origin, and let's say in this case the dipole is oriented along the z direction. Dipole is oriented along z direction. Okay, so now we want to write the electric field lines associated with this dipole. Electric field lines of this associated with the field of this dipole, and we want to write this electric field line equation of electric field line in spherical polar coordinate system. So for that, consider a point, this space, let's say P point, which coordinate in spherical polar coordinate system, let's say r, theta and phi. R, theta and phi. So r is the distance of this point from the center of the dipole. Theta is the angle between this dipole, z-axis, and this r. In this case, dipole is oriented along z-cap, so it will be directions between our dipole and this r vector. And phi, as we consider in spherical polar coordinate system, if we take the projection of this r vector in the xy plane, this projection, the angle between this projection and this positive x-axis is called phi. Phi. So later we'll see if we place a dipole like this. So in this case, at any point, if we calculate electric field or potential, we'll see the electric field and potential will be always independent of phi. Independent of phi, so it will be only function of r and theta. Why it is so? Then when we calculate this electric field, maybe after few classes we'll learn how to calculate electric field and potential because of a dipole. In that class, we will discuss why this electric field and potential due to a dipole will be independent of phi. So at this type of moment, just assume or just believe that the electric field or potential associated with the dipole at any point P, whose coordinate is r, theta, phi, will be always independent of phi. It will be only function of theta. Only function of theta. So in second example, what we are going to do here, so we want to write the equations of electric field lines due to a dipole. So write here electric field lines equations of electric field lines in due to a dipole. Equation of electric field lines due to a dipole. Okay. So in this case, we want to write in spherical polar coordinate system. So what is the differential equations of electric field lines in spherical polar coordinate system? So we know the differential equation. The differential equation of electric field lines in spherical polar coordinate system dr by er r d theta divided by e theta equals to r sine theta d phi divided by e phi divided by e phi. But for this dipole, as I told you, that electric field will be only function of r and theta. So field equations of field line will also be only function of r and theta. It will be independent of phi. So for that, first, if we want to calculate the equations of electric field line because of the dipole, just as we have calculated here for a point charge. For point charge, what we have done here, first we have considered a point, and then at this point we have calculated, we have written the electric field. So same way, so to write the equations of electric field lines associated with the dipole, what we have to do, first we have to write the value of electric field at this point because of the dipole. So at this moment, let me just define the electric field. If you don't know how to write this electric field because of dipole, we'll learn later. At this moment, just my intention is just to give an idea how you can use this differential equation in spherical polar coordinate system to write a differential to write a equations of electric field line in terms of spherical polar coordinate system. So for that, just write the electric field at point P because of the dipole. So the electric field at point P due to dipole is equals to 1 by 4 pi epsilon naught 2p cos theta, where p is the magnitude of the dipole, divided by r cube into r vector, plus p sine theta divided by r cube into theta into theta cap. So electric field at point P because of this dipole, and what is the position vector of P? It's at a distance r from the center of the dipole, making an angle theta with the dipole, and since it will be phi independent, so it doesn't matter what value of phi it is. Yeah, what is the value of phi of the point P? Okay, so now we know the electric field at point P. So from this electric field, we can write what will be the r component of electric field. So therefore, the r component of electric field, we can write 2p cos theta divided by 4 pi epsilon naught r cube, and theta component of electric field e theta is equals to p sine theta divided by 4 pi epsilon naught r cube. 4 pi epsilon naught r cube. So this is r component, this is theta component. Now what we have to do, we have to put this value of r component and theta component in the above equation, this equation. And since it will be independent of phi, so in this case we'll write only these two terms. So therefore we can write dr divided by 2p cos theta divided by 4 pi epsilon naught r cube is equals to r d theta divided by p sin theta divided by 4 pi epsilon naught r cube. 4 pi epsilon naught r cube. And if we simplify this, finally what we'll get a equation like this: dr divided by r is equals to 2, we can multiply here, so 2 cos theta d theta divided by sin theta, okay, divided by sin theta. So now we have separated this r dependent term and theta dependent term. So what we can do, we can simply integrate this equation. So when you take integration of this equation, what we'll get ln r is equals to 2 ln sin theta plus some integration constant. Again, we can take in terms of ln, so ln c. So from here, if we remove the log from both sides, then what we'll get r is equals to c sin square theta. C sin square theta. So this is the equations of electric field lines. Electric field lines due to a electric dipole in spherical polar coordinate, where r is the distance of the point P from the center of the dipole, and theta is the angle between this r and dipole. Theta is the angle between r and dipole. Okay, where c is the integration constant. The value of c can vary from 0 to infinity. 0 to infinity. Okay, so now if we want to draw the electric field lines, so what we have to do, we have to draw this curve for different value of c. For different value of c. So first case, let me just draw it again this here. So we have x-axis, let's say this is our z-axis, and then this is our y-axis, and this is our x-axis. X, y, and z. Okay, x, y, and z, and we have a dipole which is oriented like this. Dipole is oriented like this. Now what we have to do, we have to draw the electric field lines associated with the dipole, and already we found the equation. We have written the equations of this electric field lines, and that equation is r is equals to some constant into sin square theta, where this constant is, in this case, it can have value from 0 to infinity, any value between 0 to infinity. Okay, so for simplicity, if we say, let's say c is equals to 1, and then if we want to draw this curve r is equals to, then what will be the equation? If we put c is equals to 1, we'll get r is equal to sin square theta. R is equals to sin square theta. So now if we take different value of theta, we'll get different r, and then if we added them, we'll get a curve. So for c is equals to 1, we'll get r is equals to sin square theta. Now if we put if we take a point, or if we say theta is equals to 0, in that case r will be 0. R will be 0. So on any point on the z-axis, the value of r will be 0. Theta will be 0 on the z-axis, so r will be 0. Now if we mix the angle, if we increase the value of theta, So up to 90, R will increase. So as we'll increase the value of theta, R will also increase. So we can draw like when theta is equals to on the 0, then R is equals to 0. Now if we increase the value of theta, R will also increase. So it will goes like this way. And then at particular when theta is equals to 90, that time this R will be maximum. R will be maximum. And after then again on the opposite side, I mean bottom side, the above of the xy plane, it will be look like this, and the bottom side of the xy plane, the value of theta will now, it will goes from pi by 2 to pi. So between this pi by 2 to pi, the value of sine theta will decrease. So R will also decrease, and when you put theta is equals to pi again R will be 0. Sine pi is 0. So then it will be look like this. Yeah, it will look like this. Then if we put c is equals to 2, then it will be look like this. If we put c is equals to 3, then it will look like this. If we put c is equals to 4, then it will look like this. If you put 5, it will look like this. So on, if we increase the value of c, the curvature of this curve will also increase. And when we put c is equals to infinite, c is equals to infinite, then we'll get a straight line parallel to the z-axis like this. In this case, radius of curvature will be infinite, so it will become a straight line. A straight line. So now this is a particular value of phi. We have drawn the relations between r and theta. So since this electric field will be independent of phi, so if we change the value of phi, this curve will remain same. So any other directions also, the relations between r and theta, this curve will be the same shape. So in this case, if we draw opposite direction, I mean the opposite value of phi, whatever the value of phi in this direction, if we take another point where the phi is just opposite value, this opposite side of this point, then it will look like this. See 1, 2, 3, 4, 5, 6. And then it will look like this. Okay. So it will look like this. Okay. And I think from 12th class also, you know, if you draw electric field lines of a dipole, it will always look like this one. So now we know the differential, we know the equations of electric field lines. So from these equations, if we draw the electric field lines, we'll get exactly the same figure as we used to draw from our 12th class and high school physics. Okay, so now at least from these two example, I hope you get some idea how to use this differential equation, and using this differential equations, how one can write the equations of electric field lines associated with different charge. So for any kind of charge, if we want to write the equations of electric field line, then what we have to do, first we have to consider any arbitrary point. Depending upon if it is rectangular coordinate system, then we will consider point xyz. If it is spherical polar coordinate system, then r theta phi, and cylindrical coordinate system, rho phi z. And then what we have to do, whatever the charge distribution will be given, because of that we have to calculate the electric field at that point. And then we have to write the different component of electric field, and after then if we put this component of electric field in this differential equation, and then if we integrate these equations, we will get the equations of electric field line. And in this case, we have calculated electric field line because of a point charge. These equations will be a set of parallel line which will passes through the origin. And also we have drawn electric field lines associated with the dipole, whose equations of field lines is r is equals to c sine square theta, where c is some constant whose value will vary from 0 to infinity. And if we draw this curve for different value of r and theta and phi, we will get a figure like this. We'll get a figure like this. Okay, so now we know what is the definitions of electric field line, and what are their mathematical equation, mathematical representation. And again, if we want to draw this, practically, if we draw this electric field line, then what we have to do, we have to place electric field here, dipole here, and then if we place a point charge in this region, so you have to, if we place this point charge here, which is movable unit positive charge, this charge will follow this path. If we place here, then this charge will follow this path. And if you here, if you connect this all this point of its path, it will give you this type of curve. So that is the way how you can draw a practically this electric field line associated with any charge. And if you want to write the mathematical equation, then simply you can do, you have to consider arbitrary point. At that point, you have to calculate electric field, and then you put the value of different component of electric field in the differential equation, and from there you can get the relations between xyz or r theta phi or rho phi z. Okay. Now next, what we have to learn, what are the properties of these electric field lines? What are the properties of electric field lines? So right here, properties of electric field lines. Properties of electric field lines. Yeah. So first properties of electric field lines is that it is started from the positive charge. These lines are started from the positive charge and terminate at the negative charge. So right here, first property is electric field lines start from the positive charge and end at the negative charge. In at the negative charge. Then second property is two electric field lines never cross each other. Two electric field lines never cross each other. Never cross each other. If they cross each other, then what will happen? Let's say if two lines cross like this, then according to definitions of electric field lines, what we can do, we can draw two tangent on this two curve, and the tangent directions of tangent will be two different direction, will give two different directions. So that's when at this point, for same charge distribution, we'll get two different directions of electric field, which is not possible, which is not allowed. So in this case, we can say that two electric field lines will never cross each other. Never cross each other. And third, electric field lines electric field lines never forms closed loop. Never form closed loop. Why they never closed loop? Because in the first statement we written that start from the positive charge and end the negative charge. So if it is closed loop, let's say it started from here and then again it will come back ended here. So same type of, I mean, it cannot start from the positive charge and at the end of the negative charge. So there must be two. It should always started from the positive charge and it should end at the negative charge. But this suggests that if we make a closed loop, then it will suggest that it will started from the positive charge again it will end into the. It will also end at the positive charge, same type of charge. So that is not allowed actually. So that's why electric field will never form a closed loop. And if it is never from a closed loop, then what will be the curl of this electrostatic field? And of course, in this case, we are talking about electrostatic field. That is, electric field will be generated because of the static charge. Later also, we'll discuss the electric field that is called induced electric field, which will be generated because of time-dependent magnetic field. From there, we'll see its opposite kind of nature. We'll see that induced electric field can form a closed loop, but static electric field will never form a closed loop. So now if the static electric field never form a closed loop, then what will be the value of curl of electrostatic field? It will be always 0. It will be always 0. As I told you, when we talk about the curl of any vector, so curl actually, if we operate this curl operator any vector field, that will give you the rotational nature of the electric field. Rotational nature of this vector field. If it is rotated about some axis, then only the curl of this vector will be non-zero. But since electric field lines never form a closed loop, so in this case there will be no rotation of electrostatic field lines. So because of that, we can say the curl of the electrostatic field will be always 0. Curl of the electrostatic field is always 0. And then fourth property is, let's say we have a positive charge here and we have a same amount of negative charge here. Then what will happen if we place a let's say we want to draw the electric field line practically, then what we have to do, we have to place a point charge here which is freely movable. So now this positive charge will repulse and this negative charge will attract this unit charge. So because of that, this charge will move along this direction. So now if I release this point charge instead of this point, if we release here, then it will repulse in this direction and it will attract along this direction. But since initially repulsive force will be large compared to the attractive force, so it will start moving like this, and then after some times this force because of this negative charge will dominate. So because of that, charge particle will start moving towards the negative charge, and sometimes it will fall on the negative charge. Same way, if we place here, then it will goes like this way. If we place here, it will goes like this way. If we place here, it will goes like this way. So you see, so in this case, from positive charge to negative charge, if the electric field line is continuous, electric charge is continuous, and since it in this case it is started from positive charge and ended at negative charge, so we put an arrow like this. Okay. So now if we assume that we have a positive charge here and negative charge at the infinite, at the infinite, then what will happen? So from positive charge, electric field line will appear and it will goes up to infinity in all direction. In all directions it will goes like this. So in this case, all these lines will be continuous up to infinity because it will end at the negative charge, and negative charge is placed at the infinite distance from this positive charge. So all these electric field lines will be continuous up to infinite until we place a conductor. If we place a conductor in their path, then what will happen? So later we'll see the conducting medium. Inside the conducting medium, electric field is always zero. Inside the conducting medium, electric field is always zero. So because of that, there will be no electric field inside the conducting medium. And if there is no electric field, then what will be the directions of electric field? Nothing. So we cannot define the directions of electric field. So that's why electric field does not exist inside the conducting medium. So fourth property is write this this way. Electric field lines are continuous line until we place a conductor in their path. Okay, in their path. Then it will be infinite. It will be continuous line. Okay. So these are some properties of electric field lines. Electric field lines started from the positive charge and entered the negative charge, and then electric field lines, two electric field lines never cross each other, and electric field lines never form a closed loop, and electric field lines are continuous line until there is a conductor in their path. Okay, so far we have learned the electric field lines, definitions of electric field lines, their mathematical representation, and we have also learned how to draw the electric field lines practically, and mathematically if we want to write the equation. So from this differential equations we can calculate, we have also learned how to calculate the equations, mathematical equations of electric field line associated with different charge. So now we'll talk about electric flux. So once we have the idea of electric field lines, so now we'll talk about electric flux. Electric flux. Electric flux. So flux means something flow out. In this case, electric flux means flow out of electric field line. Flow out of electric field line. It's because of some charge distribution in this region we can represent the electric field. So these are the electric field lines in this region. And let's say consider one surface here. Area vector along this direction. And the angle between this electric field and this n cap is theta. N cap is theta. So now what we have to do, we want to define the number electric flux through this surface. What will be the electric flux through this surface? So how we define this electric flux through the surface? So first write the definitions of this electric flux, how it is defined. The number of electric field line, the number of electric field lines pass through a surface perpendicular to it, it's called electric flux of the surface. It's called electric flux that surface. Okay. And how we define this flux in mathematically? So for that, equate this, let's say this is electric field, and elementary area on this surface is, let's say, ds vector. Then we define the flux through this surface is equals to, so we have to see the number of electric field line perpendicular to the surface. So you have to take the position component of electric field parallel to the area. So we can write simply E dot ds vector is component of electric field along the directions of area vector. So first we have to take the dot product, and that will give you the flux passing through this elementary area. And then if we integrate over the surface, that will give us the total flux through this surface. Total flux through this surface. Total flux through this surface. And let me also define one more thing from here. So the flux passing through this elementary area can be written as d phi is equals to E dot ds, and then if we divided both sides by the ds, and if we take the magnitude, then what we'll get, d phi by ds is equals to mod of E. Mod of E. So d phi is the flux through the elementary area ds. So d phi by ds means flux per unit area, that is flux density. Flux density. So flux density is directly proportional to the amplitude of the electric field. At any point, the flux density will be directly proportional to the amplitude of electric field. Okay. So now you see, so using these two concepts, that the electric field lines drawn in such a way, the tangent to this curve is give the directions of electric field, and the density of these field lines, that is the number of field lines passing through unit area, density of electric field lines is proportional to the magnitude of electric field. So that's mean from these two concepts, the concept of electric field line and the concept of electric field line density by electric flux density, we can represent the electric field by the field line. We can represent a complete nature of electric field by the field line. So what does mean? It means that let's say we have an electric field which is uniform. That's when the magnitude of electric field is everywhere same, and the direction is also in same direction. So in this case, we can represent this electric field line by a set of parallel lines. By a set of parallel lines. So if we put a tangent, directions of tangent in this direction, so this will give the directions of electric field, and the density of electric field line, that is the number of field line passing through per unit area at any point, give you the magnitude. So in this case, you see, if you consider any point here or anywhere, the number of electric field line passing through unit area will be always same. So this type of field is called uniform electric field. So that's mean we can represent a uniform electric field by a set of parallel lines, by a set of parallel lines. And also we can represent this non-uniform electric field using the concept of electric field lines. So if it is uniform, then magnitude of this electric field line will be same at everywhere. That's mean flux density will also be same. But if it is non-uniform, then flux density at different point will be different. But the magnitude of electric field is high, then flux density will be high. The magnitude is less, flux density will also be less. So if we want to draw a non-uniform electric field, then we can represent like this way. We can write this way. You can see at this region, the number of field line density, flux density is high. That's mean magnitude of electric field will be high. And in this region, the flux density is less, so magnitude of electric field will be less. So this is the uniform electric field. Uniform electric field. And this represents non-uniform electric field. Non-uniform electric field. Okay, non-uniform electric field. Okay, so I hope you get some idea what is electric field lines, how we can represent mathematically, and what are their properties, and how they are linked with the electric flux. Electric flux. But the main thing that we have to keep in mind that the definitions of electric field line and the concept of flux density, combine these two, we can represent the electric field line. Either it is non-uniform or could be uniform. It is uniform, then everywhere magnitude and direction must be same. So we can, in this case, we can represent a state of parallel lines. And if it is non-uniform, then at different point flux density will be different, and as well as direction can also be different. Direction can also be different. So in this case, you can see here, in this point electric field along this direction, but here electric field is along this direction. So at different point electric field directions may be different, or magnitude could be also different. So this type of electric field is called non-uniform electric field. Okay, so next class, in next class we will learn how to calculate this flux for different type of situation. What type different, when I say different type of situations, mean you see that a flux through a surface is just, we have what, if we want to calculate flux through any surface, then what we have to do, we have to take the dot product of electric field and area. Now this electric field can be uniform, can be non-uniform, and also the area vector over which we have to take the surface integral to calculate total flux. That could be closed surface or open surface. Closed surface or open surface. And also sometimes examiner give us instead of giving the electric field, examiner give us a charge distribution, certain charge distribution plus a closed surface, and then they ask what will be the flux through the closed surface. So for this type of concept we'll discuss in the next class. We'll see how using the Gauss law we can calculate flux and electric field line, electric flux and electric field. So that we will discuss in the next class. Okay, so in this class I hope you get this idea, what are electric field lines, what are their mathematical representation, and how we can write the equations of electric field line using the differential equation and their properties, and also the concept of electric flux. Concept of electric flux and how the flux density is associated with the magnitude of electric field. So in next class, we'll learn how to calculate electric flux for different type of situation, as well as we also discuss the concept of Gauss law and its application. Okay, so thank you for watching. We'll see you in the next video.